So welcome everyone. Good morning. It's my great pleasure to welcome you to the second distinguished world seminar at UMN. And it's my great pleasure today to welcome Dr. Tian-Jian Hsu. Tian-Jian is currently a professor of civil and environmental engineering at the University of Delaware and the director of the Center of Applied Coastal Research. He got his bachelor degree in ocean engineering from National Taiwan University in 1994. And he got his PhD degree in civil engineering from Cornell University in 2002. He has worked as a researcher at Woods Hole Oceanographic Institution and assistant professor at the University of Florida before he joined University of Delaware. He has won many important awards, including the NSF Career Awards in 2007. And 2 years ago, in 2021, he won the Hans Albert Einstein Award. As many of you already know, Hans Albert Einstein is the son of the most famous Albert Einstein. Actually, Albert Einstein used to study sediment transport. So when Hans told his father that he wanted to study sediment transport, Albert Einstein told him not to do so because sediment transport was an intractable problem. But Hans didn't listen to his father. He continued to study sediment transport and became an outstanding researcher. And in recognition of his outstanding contribution to the field of sediment transport, people established the Hans Albert Einstein Award. So for any people who study sediment transport, this is a very prestigious award. And Tian-Jian got this award for his outstanding contribution in computational numerical simulation of various sediment transport problems. He has published about 100 peer-reviewed papers and book chapters. He will only cover a fraction of it today about the role of turbulent coherent structures on evolving seabed. It's my great pleasure to welcome Tom Hsu today. So if you have any questions, you can type in the chat or just raise your hand or save it to the end of the seminar. So without further ado, Tom, the floor is yours.
Thank you. Thank you so much, Judy, for such a nice introduction and kind word. It is my great pleasure to be here today, I guess here, virtually here, to give this prestigious seminar. And I again want to apologize that I cannot join this in person, which I regret, but I hope you guys are doing well after the snowstorm. In fact, Judy gave a very good introduction, sort of motivation of my talk. I'd like to talk about the importance of resolving turbulent coherent structures in modeling several coastal sediment transport problems. And the reason I mentioned that is because, you know, I think the side story continued with what Judy was just saying was Albert Einstein kind of discouraged his son of doing sediment transport research. I think particularly is because at that time, because there's no fast computers. So from Einstein's perspective, you know, solving turbulent flow problem is extremely difficult. It's a highly nonlinear problem. But I guess he I don't know, he couldn't foresee the rapid growth of computing technology. So I guess we all benefit from it. So today, myself, or including many outstanding researchers in Minnesota, are able nowadays to try to solve turbulent flow problem by using computational fluid dynamics, which is a very useful tool to tackle nonlinear problems. So we are able to say, now we can start resolving turbulent coherent structures. So enough said, it is very important. And I would like to provide you with a few examples today relevant to coastal sediment transport problem. First, I'd like to acknowledge that today's talk is really contributed by my postdoc, Antoine Mathieu, two senior graduate students, Benjamin and Jia, and also Julien Chouchet and his team at Lagi in France is our long-term collaborator on modeling coastal sediment transport. to move the slide. Okay, so as I already mentioned, sort of the motivation here is that nowadays, if you look at most of the coastal estuary modeling community, I would say predominantly we still rely on the so-called Reynolds average methodology or RANS, because it's really still the most affordable approach when you need to look at a larger scale problem. Of course, the main assumption, or I would say the big assumption in the RANS approach is that we're trying to model the entire turbulent fluctuation based on a diffusion process, and hoping that with this diffusion type of closure, we're still hoping that the ensemble averaged mean flow structure can be resolved very well. Of course, this has been proven to be true for shear flow in a relatively simple configuration, that the turbulent diffusion is actually able to do a good job. However, the concern right now is that when we are looking at flow that's more complex, for example, flow with instabilities, in this case, you see the generation formation of ripples that cause flow separation and vortices. When you have this kind of more complex situation, the concern is that can the Reynolds average approach which actually force a separation between the resolved mean flow structure from the turbulent energy cascade. Is that good enough? For example, in this, let me play this animation again. This animation is generated by the model that I'm going to introduce later called SAFON. It's a two-phase model to model sediment transport, but this particular simulation is based on the eddy viscosity K epsilon or K omega type of closure. As you can see that with this RANS approach, we do resolve the vortices around the ripple. Okay, but it's kind of interesting. This will be interpreted as Reynolds average or ensemble averaged vortices. And then the entire energy cascade process will still have to be parameterized by the turbulent diffusion. So the question is that, where is that demarcation line between the so-called ensemble averaged vortices and the corresponding coherent structure and their cascade? It is difficult to judge where is that cut, and also can all the existing two equation model, for example, really doing a good job parameterizing the right amount of so-called turbulent diffusion so that the resolved vortices is indeed sufficiently accurate. So those are the concerns. So today, we actually hypothesize that, on the other hand, if we start with the turbulence resolving approach, that at least can resolve the larger coherent structures using the so-called large eddy simulation, this may be a more appropriate choice. Okay, so I like to kind of also point out, sort of motivate the study using our recent effort on a sort of on a nearshore hydrodynamic problem to just show you that for coastal flow problem, it is indeed characterized mostly as a complex flow situation. So therefore, a large eddy simulation is probably a much better approach. So here you see, this is actually a video taken from a few years ago, our large wave flume experiment carried out in the Oregon State University. They have a 100-meter wave flume. The goal of this study is to study beach erosion during the extreme storm and surge event. In fact, in this case, this whole experiment consists of about 40 trials. Each trial is about 20-minute long. And so here you see this video from a particular trial. And we're trying to sort of model the rising stage of the Hurricane Sandy. This beach was modeled based on the Mentolocking Beach at New Jersey during the Hurricane Sandy. But this is a sort of a 3-to-1 scaled down laboratory experiment. And this entire 40 trial actually consists of 3 regimes during the surging of a storm. start with the erosion of the berm, and then also lead to a formation of a bar in the inner surf zone. And then the second stage, we start to see the growth of this bar in the inner surf zone, which actually protects the beach. But eventually, because during the storm, the water level keep increasing, eventually the water level reach the dune, and we start to see the dune erosion. And so today, I'm not really going to talk about this experiment, but I just kind of want to show you one numerical simulation using large eddy simulation based on OpenFOAM that show you the berm erosion stage. So here you see the quick animation about the simulated wave breaking over this berm. And using the large eddy simulation, the numerical model tool we use is actually OpenFOAM. You see this very intense interaction of wave breaking at the swash, and then this wave breaking generates what you see, this gray color are how we identify the turbulent coherent structure using the Q method. You see the turbulent coherent structure generated at the breaking wave, but this is really shallow, right? So when the breaking wave is approaching the shore, you see the breaking wave coherent structure actively interacting with the bed, which may cause significant sediment transport. And if you look at this particular picture, sort of a zoom in the swash, you see that in this early part of the storm, the wave actually breaks very close to the shore. And we see a very strong interaction between the backwash of the previous wave interacting with the incoming flow that generates a lot of very high bottom shear stress and turbulence. And what happened is that this strong interaction in the sort of a complex swash motion, backwash interacting with the incoming wave, probably caused a large offshore sediment transport that's eroding the berm. But of course, this is a pretty high resolution computational fluid dynamics simulation. What I show you here is that there's no sediment transport. It's just simulating the hydrodynamics. So when we move on to actually simulate this morphodynamic change, right now we still have to use this very popular wave averaged, wave group resolved nearshore hydrodynamic and morphodynamic model called X-Beach. Here you see that if you compare the X-Beach simulation with the measure data and our previous large eddy simulation data, you see that the model is doing a very good job in predicting the decay of the wave height, even the setup. Okay, however, the X-Beach model significantly over-predicts the undertow current in the inner surf and the swash that I just showed you in the previous slide. But this is a problem because undertow current, as we know, is the main driver for offshore transport. But now you see X-Beach is significantly over-predicting it. On the other hand, if you look at two important nonlinear wave statistics that drive sediment onshore, they are the wave asymmetry and the wave skewness. Wave skewness is predicted reasonably well, but the wave asymmetry, again, in X-Beach has been significantly over-predicted. And while in the end, if you look at the bathymetry, you see that X-Beach, if you look at this part, the X-Beach over-predicts the formation of this offshore bar due to the dune erosion. But this shouldn't be surprised because the X-Beach actually over-predict the undertow, right? But interesting thing is that even with the over-prediction of the undertow, you see X-Beach still under-predicts the berm erosion quite a bit. And so we actually hypothesized that this is probably because X-Beach is an average model, right? So it really cannot resolve intra-wave processes and the turbulent processes. So we believe that we hypothesized that X-Beach didn't do a good job on taking care of the effect of wave breaking turbulence on the sediment transport, and therefore there's still a problem with the predicted bathymetry. So this is kind of my motivation. And of course, in the long run, if we want to deal with this problem, we will have to rely on a turbulence resolving approach that really resolve the breaking wave turbulent coherent structure and how they interact with the seabed. Okay, so enough of the motivation. So today, I like to use a turbulence resolving two-phase model to study several sediment transport processes. And three examples I'm going to show you. The first one is the wave-driven shear flow, but particularly I like to emphasize shear flow for fine sand. And the second problem is a scour problem of a vertical pile. And the third problem is the initiation of backflow. All three problems what I'm showing you today that actually require resolving turbulent coherent structure. If you use the traditional Reynolds model that take care of the effect using diffusion, turns out it doesn't work. So just want to very quickly okay, sorry. So just want to very quickly show you the numerical model that I'm going to show you use today. The model is called SATFOAM. It is an open source Eulerian two-phase model for sediment transport application, again, created in the OpenFOAM framework. This SATFOAM solved the water phase and the sediment phase with their own momentum mass and momentum equation for their individual water phase and the particle phase. And then the coupling between these two phases is through this interface momentum transfer term that usually we model it as a drag and the pressure gradient. Another important thing about this two-phase model is that we can take care of the particle stresses. In the model itself, we take care of the particle stresses based on two parts. In the more dilute part, we have shear-driven collision that can be taken care of by kinetic theory or the mu-I rheology. But in the more concentrated part of the sediment, we have the quasi-static friction contact model. And recently, we also add dilatancy effect into this model. And the important thing about this type of model is that this kind of two-phase model framework really allow us to avoid this artificial separation of transport into the well-known bed load and the suspended load. So we can pretty much model the entire transport altogether. And so therefore, it is really useful for us to study the response of the seabed, particularly the interaction between, for example, the structure and the seabed. For example, what you see on the right, we have a pipeline that directly touch the seabed in this two-phase model. And if you do scour research, you probably know that if you do a single-phase model, you will have a problem to have the structure directly interacting with the seabed. But for two-phase model, there's no problem. And then in this case, we can simulate the flow goes through the sort of the porous seabed underneath the structure, eventually causing piping phenomena, which is a well-known phenomena for the onset of the scour. So this is sort of advantage that you can really use a two-phase model to deal with this problem. But going back to turbulence, as I mentioned, the early part of our studies, since about a few years ago, this model is only based on Reynolds-averaged approach. So we have K epsilon, K omega closure, but more recently, we are able to develop this model into 3D logic simulation with the dynamic procedure to close the stress in the fluid phase and the particle phase. Okay, so the first problem I like to sort of introduce is the so-called phase lag effect and the net transport for fine sand driven by nonlinear wave. So first, let me just mention that we're interested in this transport mode called shear flow. This is usually what happens in the very energetic surf zone and the swash zone because the non-dimensionalized bottom shear stress or called shear parameter is usually much greater than 1. And a researcher in coastal community is actually knows very well that shear flow occurs between median sand and the coarse sand. So here, when I say median sand, it's about 0.2 to 0.3 millimeter in diameter. Coarse sand maybe 0.4, 0.5 millimeter. The shear flow transport for this kind of a median coarse sand is well understood. But what puzzles coastal engineers is that when we look at shear flow for fine sand, okay, here when I say fine sand, it's about 130 micron to about 200 microns. So it's sort of the finer part of the sand that you usually see in the beach. So it's still not cohesive, but it's sort of a finer part of the sand when you go to the beach. So it turns out for those fine sand, their shear flow characteristic under wave is very unique, and it's very different compared with median and coarse sand. First of all, typically when we drive the sediment transport with onshore velocity screw wave, such as the Stokes wave that you typically see in a shoaling wave, for median and coarse sand, we obtain onshore sediment transport. That's well known. However, it is well known from the laboratory experiment, if you see the red box here, that for fine sand, typically for the grain diameter smaller than 0.15 millimeter, we actually see an offshore transport driven by onshore velocity screw wave. So that puzzles people a lot, and because the transport direction is completely different. Another thing researcher recognizes that for fine sand, the normalized shear flow layer thickness is actually much, much larger compared with the median and the coarse sand. And that's also something puzzles people. And more important thing is that when people use the typical Reynolds-averaged model to model fine sand, they cannot reproduce these two important phenomena. So here, we're trying to use this SAFON, the two-phase model, but run with a 3D logic simulation and try to see if we can reproduce the fine sand phenomena. Because our hypothesis is that this unique feature that we observed previously, the offshore transport and much larger shear layer thickness is probably caused by the interaction between the instabilities, turbulent eddies, and the sand. And so we also kind of validate our large eddy simulation model with the YouTube data reported by O'Donoghue and Wright. But they actually report both the median sand and the fine sand. And first, let's take a look, see how the model can reproduce the measured sediment concentration profile. In this case, they are all under a sine wave. What you see here is that the model for both median sand and fine sand generally can reproduce the sediment concentration profile under different phase of the wave. More importantly, if you look at the fine sand result on the right, you see that the model is able to reproduce this interesting shoulder feature of sediment concentration. And more importantly, if you look at the transport layer thickness, the model is able to reproduce this large transport layer thickness unique for fine sand. Particularly, if you sort of looking at this, just focus on the flow reversal here. Here I show you two snapshots. The left is for median sand and the right is for the fine sand. You see the two color here. This gray color is the isosurface of sediment concentration of 8%. And then there's a darker color, brown color is the isosurface of 57%. Okay, so for example, you see that for median sand at the flow reversal, you see the isosurface of 8% and 57%, they basically coincide with each other. This means that there's not much sediment suspended during flow reversal. And in fact, above the sediment layer, you see some small turbulent coherent structure remaining in the water column. But for fine sand, you see that this is probably because of their small settling velocity. The sediment remains suspended even during flow reversal, and there's really not much of a turbulence at all. Okay, but then if you move on to the next phase, that is during the acceleration phase, you see that some sediment start to get suspended for median sand, and we see more turbulence. Interesting thing is that if you look at fine sand, you see that between the 8% and the 50% layer, there's a generation of this kind of a roller type of turbulent coherent structure. We analyze this and we are sure that this is some kind of instability generated in unique for fine sand, but it doesn't show up in the median sand. And what happened next is that this instability actually grows, eventually leading to stronger turbulence, and you see much more sediment is suspended. And in fact, if you go to the next phase, that's during the deceleration phase, you see that the distance between the 8% and the 57% isosurface are really large. And this actually is a really large transport layer thickness, unique for fine sand. But if you look compare with the medium sand, the thickness is much smaller. Okay, so generally we believe that our model really reproduce what's being observed between the difference between the median sand and the fine sand, and more importantly, the sheet layer thickness, which apparently is related to the generation of instability, that's very unique, but that could be reproduced by the large eddy simulation model. So in summary, the major finding is that researchers have tried to explain this unique feature of fine sand, and as I said, they call it phase lag effect. But traditionally, without this detailed numerical simulation, what people can recognize is just that, oh, fine sand has a smaller settling velocity, and therefore there's a stronger phase lag effect. But what we really see is that this fine sand, not just because of their small settling velocity, is also because there's stronger sediment turbulence interaction that actually generates flow instabilities during the flow reversal and the acceleration phase that lead to a burst of transport that further cause sort of a phase lag effect, right? So phase lag effect could be contributed by both. That is not just the small settling velocity of the particle, but also the fact that now the transport layer thickness is bigger. But that transport layer thickness is bigger is because of the flow instability. And you can only obtain that by resolving that by resolving that onset of instability and then the subsequent growth into turbulence. And just very quickly, and now we try to drive the model with a onshore velocity skewed wave, typically for the surf zone. And then we do show that now we can obtain the expected offshore transport for fine sand. And turns out what happened is that if you look at the blue area here, is for fine sand, this is where the phase lag effect becomes important, which actually is pronounced during the offshore flow reversal. You have a very strong phase lag effect. So sediment didn't really settle. But that's the time when those suspended sediment get swept offshore and causing the net offshore transport. So they are all related because of that instability. So I don't have time to go into the detail here. This is a paper that we just submitted to coastal engineering. And so now I'd like to sort of move on to another, I think is a very interesting problem that requires resolving turbulent coherent structure is a scour problem. So particularly, I like to look at the scour around a vertical pile. As you know, nowadays, we worry about scour of beach pier, and nowadays we're building a lot of offshore wind farm. And those kind of structures can be typically modeled as a cylindrical pile. That's why we are interested here. And just from this review paper, you see that there's a variety of vortices generated around this kind of vertical pile, particularly something called sorry, couldn't see here, something called the horseshoe vortices is very important in driving the development of scour hole. So our concern right now is that, okay, so if the generation of those vortices is so important driving the scour hole, then the question is that, is it important to be able to concurrently resolving the generation of those vortices and their subsequent evolution as a coherent structure in the energy cascade processes, or it doesn't really matter, just use Ray's model and plug in some turbulent diffusion. Okay, so those are the concerns. So we're gonna do some intercomparison between the large eddy simulation and the Ray's K omega closure scheme, and see how they affect the result of the flow field and the corresponding development of scour hole. Sorry. And then we're comparing with a benchmark experiment reported by Sumer. He actually has two sets of experiments using 0.717 millimeter sand. It's all driven by wave. With a vertical cylinder, but one experiment, there's no sediment, so he can measure the bottom shear stress using hot film. The other set of experiment, you actually have sediment, and he can measure the scour. This is the mesh that we set up using our cell phone. Just want to point out that we try to use similar grid size, but not exactly the same between the RANs and the large eddy simulation so that we have a fair comparison. And so here, just on the right, just quickly show you the animation. This is from the large eddy simulation, that the flow goes back and forth and causing the generation of skull hole at the bottom around the structure. And then the green color is the generation of the coherent structure visualized by the Q method. You see that the large eddy simulation really generates a lot of, I don't know how you call it, but in this case, vortices or coherent structures that lead to the very much deeper, very deep skull hole. And if you look at the comparison of the temporal development of skull hole, you see that the red color, which is the large eddy simulation result, actually predict the development of skull hole, which agrees reasonably well with the measured data. This is the measured data, but kind of fitted with the empirical curve. The trend follows with each other. However, if you look at the green curve here, this is a result from the RANS K omega model. You see that the K omega model really significantly underpredict the development of skull hole. So the question is, why is that? So first, we compare with the time average measured bottom shear stress distribution around the cylinder. You see that if you look at the K omega model result, this is actually we show two K omega model results. One is an earlier work based on Bakao. It's actually a single phase RANS model, and our own RANS model based on two phase. You see that both RANS model under predicts the sort of the significant drop of bottom shear stress close to the structure. However, if you look at our LES result or another study which used a DNS but for clear fluid, once you start resolving turbulent coherent structure, you see that you can actually capture the sharp decay of bottom shear stress. So you kind of get a hint that, okay, yes, so RANS model kind of underpredict this shear stress close to the structure. Probably that's the reason leading to an underestimate of skull hole. But the question is, what caused that really sharp change of bottom shear stress? We just looking at a visualization of the snapshot of coherent structure, you see why. On the right, let's look at it. On the right is the LES result. You see, in this case, flow going from the right to the left. So flow impinge on the structure, and you see the generation of a variety of vortices, particularly the generation of a Hsu vortex around the structure. And by the way, this is not even the highest resolution that we use. I think now we have even higher resolution, but you still see the very nice reproduction of the expected Hsu vortices that drive the skull. But if you look at the same simulation using RANS model, you see using the same. In fact, right now here, the Q, we actually dropped the Q to 1,000. So it's 4 times smaller. We still barely see the Hsu vortices. So clearly, I think what happened in this case is that this is a very complex problem, right? But the RANS model, even with K omega closure, which is considered the most advanced, probably has too much diffusion that kind of smooths out the resolved vortices. But in this case, that really lead to a significant underprediction of skull hole. Okay, so I'd like to just wrap up by showing you quickly a more recent effort. That is, we try to use large eddy simulation with cell phone to study the initiation of bed form. I like to phrase it as like a chicken egg problem, right? So the idea is that typically, if you look at people study bed form, they use stability analysis or RANS model, but usually they will have to simulate the development of bed form by initially perturb the bed with some kind of defect or some kind of perturbation based on some stability analysis, so that they can start to see the development of bed form. But if you look at earlier study by Jim Best, he argued that bed form can be actually generated by turbulent coherent structure, just by turbulent coherent structure, from a completely flat bed. Okay, and in fact, this has been proved recently by a fully resolved simulation. So this fully resolved simulation really resolve everything, flow around particles, and then they simulate millions of particles. But in this case, so this is a very important work published recently. They show that the coherent structure itself can generate baffle. But because this is a fully resolved simulation, their Reynolds number is really low. Okay, so what we try to do here is trying to use logic simulation with Cephon and start with a completely flat bed. And we like to use play with a higher Reynolds number. So we actually try to reproduce a laboratory experiment by Venditti and Church that has a Reynolds number pretty large, 76,000. And the good thing is that they measure velocity profile and the Reynolds stress, and our model can reproduce those turbulent quantity. But here's the animation. You see that this is a pretty fast process. Start with some smaller features, which I'll show you more later. But very quickly, in about 40 seconds, you develop into this more flow quasi 2D bed form. But I just want to point out, this is still in the transient process. Okay, so in the real experiment, if you run this for 30 minutes, eventually the 2D bed form becomes 3D bed form. But of course, this is a part that right now our logic simulation cannot afford to do it. But just so we only focus on the initial part. So you see that we start with the flat bed. At about just 1 second into the simulation, you see this streak type of structure. This is the color represents the bathymetry. So you start to see that the bed form initially is parallel to the flow. It's like a sand ridges. And this is actually consistent with that fully resolved simulation even though at a lower Reynolds number, they show that the existence of sand ridges triggered by the turbulent streak. And then at about 4 seconds, those streaks evolve into they call it cross-hatch pattern. And this is actually observed in the original paper. They talk about cross-hatch pattern. Here we show that we can also see this kind of cross-hatch pattern. Then by about 20 seconds-ish, you start to see those patterns become more quasi 2D uniform in the span-wise direction, which is reproduced also by our model. And just quickly, go back to follow the Jim Best's pioneer paper. He said this is because the turbulent coherent structure generates this very small, sort of a small sweep event locally that drives the defect of the bed. So here we try to just kind of bring a snapshot and plot out, first use the contour to identify the sweep event. Then we overlay that with the bathymetry at that time. This is a little bit crude. There's some history effect, but we ignore that. But just like instantaneously, the seabed and the sweep event, while we see that there's indeed a very, very good correlation. 99% of the sweep event that we identify actually is located at the trough of the bed feature. There's the last correlation. Only 60% of the ejection event is coincide with the hump. But at least for the first part, we do believe that what originally Jim Best was trying to say is consistent with what our model is reproducing. And more recently, we start to sort of extend this steady flow bed form into what we are more interested in is the bed form generated by the oscillatory flow. Preliminary results shows that similarly, I think the generation of initial generation of the bed form, even under wave, is also more like a streak type of feature associated with coherent structure. We need to look into this simulation more carefully to understand the problem fully. Just want to wrap up. The conclusion is that at least for certain coastal processes, we have to recognize that turbulent diffusion may not be the best solution. And with the progress in computing technology, I think the next generation of numerical models certainly should be based on turbulence resolving simulation approach in order to better tackle this nonlinear processes. Quick update on some ongoing and future work of further developing this open source tool, Cephon. First, is just personally, we just need to refine the logic simulation on the bed form. And recently we have some success couple the object movement, the so-called the 6DOF of object with our fluid and sediment two-phase model. Here you see a sort of a motion skull burial of an object. And recently we also have some success of including resolving the air-water interface into sat foam, so that we can really go back to study surface zone sediment transport. Here's the preliminary result. We can simulate the propagation of the wave, the back rush generating hydraulic jump, and then here the yellow represents the sediment bed. And you see, seems to me that during the back rush, you do see some burst event of sediment. Anyway, this is a very preliminary result, but we're kind of moving toward that direction, really going back to my motivation, trying to solve the surface zone beach erosion problem. Thank you very much.
Thank you so much, Tom. And this is very impressive, amazing work. So we have time for a few questions. Please feel free to raise your hand or just type your question in the chat box. Okay, cool. Tom, I think you explained everything super clear, and I'm so impressed by how your simulation, LES simulation, can explain the offshore transport and the large field of view on the decimeter scale of the platform formation. I think that's super impressive. Maybe I ask one question. I'm not a simulation person, but I'm just impressed that you can simulate the turbulence, especially interaction with the sediment grains. And to my understanding, your like closure, turbulent closure is you based on previous data, so you can kind of approximate the relationship, the like Epsilon K or like UK relationship. How do you think if you have turbulence, dense turbulence, where the space between sediment can be small, would that relationship be changed?
Yeah, that's a very good question. So I have to go back to the equation. That's what I like about this type of seminar. I can finally talk about my equation. Most of the time when I talk to coastal engineer, I don't talk about equation. Okay, so you're totally right. So in this large eddy simulation, it's not like we're much. Well, I try to criticize Rand's model, parameterizing all the scale of turbulence by diffusion. But how about our large eddy simulation? I have to be very careful here. Our large eddy simulation resolved the large eddy, the eddy size much greater than the particle size. So you're totally correct. So that's the part we resolve, and we use the typical dynamic procedure to do that. But get to the point when we get to the scale, grid size scale, or sometimes our grid size scale is just a little bit larger than the particle size. When we get to that scale, eventually we cannot resolve those turbulence. So we still need to use diffusion. And so just to answer your question, we will still rely on subgrid contribution. But as you know, typical dynamic procedure is still based on Smagorinsky. It's just that we deal with the coefficient better. So it's still a diffusion-based type of model. But I just want to point out, but that's really at a grid scale. And so we still resolve a big part of the energy cascade in the nonlinear process. And then another very important point you mentioned is the turbulence between the grain. So that's even smaller scale. Just point out, we cannot resolve the grain anyway. We model the group behavior of a grain using continuum, right? So this is because this is a Eulerian two-phase model. And so that's where, so the sort of intergranular interaction, that's phrased in terms of stresses here. The stresses here. This is the so-called intergranular stresses. When you close the intergranular stresses with kinetic theory, we are solving a granular temperature equation. So the granular temperature equation will take care of the collision, sort of granular temperature caused by the energetic of the particle motion. But in this case, we do have some kind of, I would say, semi-empirical closure that also deal with the small scale turbulence, bringing in from the fluid phase to the particle phase that kind of taking out care of the subgrid effect of turbulence on the fluid. But just what I want to say overall, because the particle we're considering is more in the, if you think about the Bagnall number, it's more between 10-ish. So the interstitial fluid effect is quite important. However, I think when the interstitial fluid effect is kind of important, usually the magnitude of the particle stress is smaller because driven by shear. It's actually dominated mostly by the turbulence that we're resolving. So to make the long story short, this is the weak part of our model that we still need to parameterize some of the small scale processes. But my experience that with the problem that I show you today, they are mostly dominated by the resolved turbulent eddies.
Yeah. Thank you so much. And I do believe that I can see your model works pretty well in these predictions.
Right. But if, like, for example, if, well, I guess what I'm saying is that I wouldn't use my model right now to do landslide, because that would be a very different situation. Yeah.
Sounds good. Yeah. Any other questions from the audience? Yeah. Okay. Any questions? You can. Oh, Michaela, you please unmute yourself.
Yes. So I have a question on the is the concentration of particles does it have some rheological properties in the way it's moving, or are you treating it like a heavy or viscous fluid? I'm losing that. I don't understand that part.
Okay, thank you. Yeah, so this is again related to this term. If you can see my, can you still see my slide?
Yeah.
Okay, so if you can see my mouse here, we have this the stress, sediment phase stress here. The sediment phase stress here actually consists of, I think it's in the previous, consists of two parts. The one part is related to shear-driven collision. So this is the part that is when the granular or sediment is being sheared, we know that the shear-driven intergranular interaction can drive the migration of particles. And this is the part I mentioned. We have two options. You can choose to either use kinetic theory of granular flow, or you can choose the mu-I rheology. And to get to your point, for very low Bagnall number, I think it's probably more appropriate using mu-I rheology, just simply by design. Because I guess that's another discussion. Kimberly is not here. She will give you much a debate about which one is better. But that's the part we're taking care of. But I also want to point out, for sediment transport, when we need to deal with the seabed, eventually sediment concentration goes to be beyond random loose packing. That's where you see the more packed bed, or the transition between the packed bed and the random loose packing. This is where shear is very small there. And so you really need to take care of sediment stress based on the enduring contact. So in this case, again, we're not using the most high-end one. We're just using some earlier frictional contact model that's typically used in two-phase flow powder technology type of thing, Johnson-Jackson. The difficulty here is that there's a lot of grand scale processes when you deal with particle in water. For example, the dilatancy effect. You know, when you shear the granular bed, you will produce suction, that kind of things. We call it dilatancy. We will have to model that in a sort of a basically empirical sense. Yeah, so that we take care of it, but not to the best degree that I think that can be further improved.
Okay, thank you.
Thank you, Tom. We have a question from Shuxu, my student. Shuxu, you're asking a great question. Could you speak out for yourself?
Okay. Hello, can you hear me?
Yes.
Oh yeah, thank you for great question. Great speech. I have a question about, because you're solving the turbulence and proving that if you're using large eddy simulations, you have better simulation about the backbone formation. So I was wondering which kinds of scale, either temporal or space scales of turbulence that is you believe is important to the backbone formation.
That's a great question. I would say maybe just go back, even though this is a Reynolds model result, but I think it's okay. So this is a very deep question, right? And the reason I mentioned that is because we're also studying this right now. There's two types of ripple. One type of ripple is driven by, it's controlled by the flow, right? So in the river, that will be the dew. It's controlled by the water depths. In the coastal environment, that will be something called orbital ripple. It's controlled by the stroke of the wave. But we also know that usually in some, depends on the condition, in the other extreme, there are also ripple determined just by the grain size. Okay, so in coastal environment, that will be called orbital ripple. And in the fluid environment, that's usually called ripple. That is scale with the grain size. And so what I can tell you right now is for ripple that's determined by the flow, I think the vortex that you resolve is the most important parameter. And that's actually a good news, right? Because that's pretty big, right? And so it's not very small coherent structure, it's the bigger structure. But my concern and the purpose of my talks today is that even if you think that it's the big vortex controlling the scale of the ripple, however, the intensity and the scale of the vortex is still controlled by the energy cascade. So if you use Reynolds-averaged model, you just use diffusion to control the energy consumption from that vortex, maybe it's not very accurate. And what we see at least in my scour simulation is that even the larger vortex that you're resolving using the Reynolds-averaged model, turns out the closure provide too much diffusion. So the intensity of the large vortex that you're supposed to resolve is still underestimated. So to make a long story short, what I'm saying is that if you think about the scale you're resolving, it's not that small, but it is the closure that kind of kills you when your closure is not good enough. Yeah.
Okay,
That's
thank you. I have a following question.
Mm-hmm.
So speaking of diffusion,
Mm-hmm.
if you we using like anomalous diffusion, which including the memory that's enlarge the time scale of the flow, will you think that will be better if we're using like another kind of diffusion to do the average?
Well, that's the $1 million question, right? So today, my talk, you can say you're criticizing Rand's type of model. Yeah, that's what I did in my talk today. But the holy grail or the $1 million question moving forward is how can we improve the closure in the Reynolds average approach in this kind of more complex flow? Today I cannot, and so far I have not addressed that issue, but I want to point out, moving forward, I think the Reynolds average type of closure is still important because we need that type of closure to deal with more important real world problem that's usually of larger scale, right? And so what I'm saying is that existing K omega model, that's what usually people think is better than K actual models, still have some issue. But I do think that with much more DNS, LES type of simulation data, we should really go back to revisit turbulence closure, especially nowadays we have AI machine learning as the tool to really allow us. You talk about this, right? You say, well, you just reduce the diffusion, maybe you'll do a better job. Yes, I think that's right. But quantitatively, how do you do it right and do it sort of a more online interactive process? I think I'm saying out loud here, but I think moving forward, machine learning could be a better way of doing this.
Thank you. Your speech is very inspiring.
Thank you.
Okay, any other questions? Okay, thank you so much, Tom. I think you studied the seminar and the semester seminar pretty well. You started with Einstein cannot predict what you are doing now. Now you are looking ahead for the next decades, AI and with more computing power. Yeah, thank you so much for this very inspiring seminar. And yeah, I just want to applaud again and look forward to more work from your group.
Thank you. Thank you very much for inviting me. Thank you, everyone. Bye-bye.